Hi, my name is Carly, and I'm a member of the RPI Engineering Ambassador Program.
Ladies and gentlemen, boys and girls, children of all ages, may I present to you a spectacle most of the morning in the making. The coolest coaster ever!
So, has anyone ever seen a roller coaster like this in real life? And why not? All of those are great reasons. This structure is way too tall and would probably not be able to support itself in real life. Throughout this presentation, we're going to talk about structures. First, we'll discuss some history about structures and how past engineers have provided us the blueprints, or the basic fundamentals of structural design that we still use today. Then we'll talk about some basic engineering concepts and factors engineers have to design around. And after that, we'll mention some current structures. And finally, we're going to talk about the future of the civil engineering industry and how you can be a part of it. The ancient Egyptians were one of the first groups of people who made several advancements in civil engineering. Imhotep was the first structural engineer to ever be documented. And almost 5,000 years ago, he designed the first step pyramid ever. Pyramids are extremely stable and are one of the few structural forms that can be almost infinitely scaled. This means that a pyramid that's 3 feet tall will be just as stable as one that's 30 feet tall. Today, we know that triangles are the strongest geometric shape because they distribute forces, like gravity, very well. The Romans were another large civilization that made many contributions to engineering. The Romans developed and pioneered concrete, a strong material we still use today. Back then, they used concrete to build large structures like the Colosseum, the Pantheon, and many aqueducts. The Romans also invented the arch, which works very similarly to triangles in that they distribute forces well. Although many past engineers, like Imhotep, made many contributions to science with inventions, some engineers made contributions by failing. What factors do you think engineers overlooked while designing the Leaning Tower of Pisa? So, what exactly happened was the soil that they built on wasn't strong enough, and so the tower began to sink on one side. To counteract this tilt, the engineers decided to build more floors. However, the extra floors weighed the tower down even more. Does anyone know what happened to the Tacoma Narrows Bridge? And what kind of environmental factors do you think could affect a bridge? What happened was there were high winds hitting the bridge, which caused the bridge to bounce up and down and to eventually collapse. And although these two structures failed, they allowed engineers to learn from their problems so that the same issues wouldn't happen again. Now we're going to talk about some of the basic engineering concepts that are used to build structures. So here we have Phineas on a bridge. There are two forces acting on Phineas. Does anyone know the force pointing downwards on him? Gravity is the force that is acting on Phineas, pushing him downwards. There is another force on Phineas called the normal force, and this is the force from the bridge that is pushing up on Phineas through his feet. The normal force is equal and opposite to gravity, meaning that when you sum the two forces together, they will cancel each other out. So at this very moment, Phineas is in equilibrium and not moving. So say, somehow, we remove the bridge under Phineas. There would no longer be a normal force acting on him, and gravity would be the only force. Now he is no longer in equilibrium, and he will fall into the river. Moments work similarly to forces in that they have to cancel each other out in order for a structure to be in equilibrium, or not moving. Moments are two forces that produce a rotation. So right now, Phineas is standing on the bridge, and gravity and the normal force are acting on him. Say we somehow move these two forces so that they are not on a similar axis anymore. One moves to the left, and the other to the right. Now, these two forces do not cancel each other out anymore, and Phineas is no longer in equilibrium. Frank Lloyd Wright designed this house, named Falling Water, to be cantilevered over a waterfall. He was able to do this because he made sure that all of the forces and moments on the house canceled each other out, and therefore the house would be in equilibrium. The Citigroup building in New York City is another example of seemingly impossible structures we can build just by equating forces and moments. The engineer had to build around a church, so he essentially designed the skyscraper to be held up by stilts. And again, he was able to do this by ensuring the forces and moments acting on the building canceled each other out and summed to zero. Engineers don't have to just design around gravity. They also need to take into account environmental factors. What kind of environmental factors do you think an engineer needs to consider in California? California is prone to earthquakes, and so engineers on the West Coast have to design for large forces that come from these earthquakes. The most popular way to do this is to add support on the bottom of the structure so that it can counteract strong lateral forces. What kind of environmental factors would an engineer consider in Alaska? Alaska is far up north and gets a lot of snow, and as snow begins to pile on the roof of a house, it begins adding a lot of extra force to that roof. So engineers in Alaska, and everywhere else that gets snow, design for heavy roof loads. And finally, what environmental factors would you consider if you were building a really tall skyscraper? Really tall structures have to take into account really strong winds. To counteract those winds, engineers design really big and thick foundations so that the skyscraper is really heavy at the base and will be less likely to tip over. Engineers also have to decide what kind of materials they want to build with. The Egg, which is located right here in Albany, is a big performing arts center with a really unique design. The Sydney Opera House is also a big performing arts center. Does anyone know what these two structures are made of? Both buildings are made out of concrete, and concrete is the most used building material because of its strength. It can also be shaped and molded to get cool shapes, as seen in the Egg. The Eiffel Tower and the St. Louis Arch are two well-known structures that attract people from all over the world. What are these two structures made of? The Eiffel Tower is made of iron, a metal, and the St. Louis Arch is made of steel, which is just a combination of different metals. Metal is also a common building material because it is strong and also gives structures an industrial and modern look. Wood is a common material used for residential projects. Wood is useful because it is plentiful, is pretty strong for its light weight, and is much easier to work with and cut than other materials. Also, many people like the warm, cozy aesthetic of wood. We said we wanted to pick materials that match our aesthetic. However, sometimes aesthetics can get in the way of practicality. Frank Gehry designed this building to have a modern look, but the reflective exterior often blinds people walking by and heats up surrounding buildings. Now we're going to talk about some new structures that have pushed the world of civil engineering to new levels. This is the Burj Khalifa in Dubai, and it's currently the tallest building in the world. How tall do you think it is? The Burj Khalifa is 2,722 feet tall, which is 44 bowling lanes stacked on top of one another. And as you can see, the structure kind of looks like a spiral, and these steps actually help deflect wind and to also decrease the wind impact as you go higher up. This is the Beijing National Stadium in China that held the 2008 Summer Olympics. Does anyone know the nickname for this structure? It is nicknamed the Bird's Nest because of its appearance. It kind of looks like a bunch of twigs set in a bowl shape, just like a bird's nest. The stadium is the world's largest steel structure and can hold 80,000 people. So where are we going in the civil engineering industry? A new movement in modern architecture is a concept called blobitecture. Computer-aided design is used to develop unique blobbish shapes, and then structural engineers and architects design the supports around the shape. This is the Sage Gateshead building in northeastern England, which is a constructed example of blobitecture. Engineers are also making developments in steel and concrete manufacturing, which will help make buildings stronger and safer. There are new technologies for concrete that will actually absorb water, and this could be really useful for roads and sidewalks. Steel is also being made stronger and longer lasting by preventing corrosion or rust. Rust damages steel and makes it more susceptible to failure. Now, although civil engineers mainly run the show, it takes a village to make these kinds of advancements. Computer science engineers are the ones developing software and programs that make designing buildings much easier. Civil engineers, as we talked about, design the structures and ensure they are safe. Mechanical engineers are responsible for any moving parts of a building, like automatic doors or elevators. Environmental engineers make sure that every engineer on the project is following important rules and codes that protect the environment from toxins and pollution. And finally, industrial management engineers act as the bosses of these projects and make sure everyone is sticking to a budget and a timeline. So hopefully through this presentation, you learned about structures and what a civil engineer does. Although the Burj Khalifa is the tallest structure standing today, maybe you'll be the civil engineer that designs the next tallest. Thank you for watching. This has been a REACH presentation. We will now move on to our hands-on activity. All right, so now we're going to be moving into our hands-on activity where you guys are going to be the civil engineers and you're going to design a house that's going to have to withstand an earthquake. So you're going to be given a few materials. This is going to be your roof. It's a piece of cardboard, and it's your job to design some sort of structure, walls, stuff like that to support this roof. And you're going to be given only 10 straws, so keep that in mind, tape, and scissors. And when you're done designing, we're going to test it on our shake table, which simulates an earthquake. So we're going to see if it will be able to withstand the lateral forces, the side-to-side forces. And then we're also going to be adding some of these weights on top of the roof to see if it will be able to withstand some force on the top. So with that being said, I'd like you to just take some of the 10 straws, the tape, scissors, and a roof and get started. I'd like you, before to actually begin, talk with your group and see what kind of shapes you might be using. Get a game plan so you're not just going into this blind. Think about some of the shapes that we mentioned in the presentation, some of those really strong shapes that we use every day in the civil engineering industry, so keep that in mind. You can begin. So I'm going to build one as well. I'm definitely going to be using triangles because those are the strongest shape, but I'm going to start by building a frame just to give myself a basic starting point, just so I'm not trying to build a bunch of triangles. So I'm actually going to cut some straw columns first just to start the frame. So I'm going to try to make them as even as possible just by lining the straws up. Definitely does not need to be perfect, but just going to do that. So, okay, there we go. So we have 4 little straw columns, and then I'm going to be taking 4 full straws and taping them all together at right angles, and then we can connect them all together, so it'll be a frame. So I'm going to be taking some of the tape and taping them all together. So I find it easier to just put one piece of tape on one of the straws first and then just kind of connecting them with that piece of tape. It doesn't need to be perfect or look good by any means, but it just needs to be able to stand up. So I'm going to connect this column to these pieces here. Okay, and then I'm going to replicate this piece. Taking one of the straw columns and attaching it to the full straw. And last one. Okay, so now we have two small frames, and then we're going to attach them together with 2 full straws. So find it easier to attach the tape right onto the piece you're going to be taping it to, and then attaching the straw like so. Like that. And then I like to do both of them at the same time onto one. Connecting that piece. If you find that you didn't do a very good job, you can just always add another piece of tape just to make sure it's really on there. So I'm going to add one more piece of tape just to make sure. Okay. And then I'm going to tape the final part on. So I'm going to tape onto this part first. Okay. And then finally the last one. There we go. So now we just have a really basic straw frame, just some small columns with the big straws connecting each other. So I'm going to go ahead and tape this onto our roof right now. So I'm just putting them on the four corners and then just taping them down. And this is just going to make it easier for me going forward to putting the triangle, the straws on to make the triangle shapes, so I was mentioning earlier. Okay, so now that's done. We have our frame on our roof, so it'll end up be going like this. Right now it's good, but again, we want to add the triangles just to make it a little bit stronger. So what I'm going to do is I'm going to take all the last four straws we have, and I'm just going to cut them in half. Again, does not need to be exact. There we go. So now we have 8 small straws, and I'm going to kind of in my head see where they're going to be located, and then we'll tape them on. So I'm going to tape them onto the corners of the frame first. So do the one side and then the other, like so. And then we're going to tape them down in the middle. And there is your triangle. So when you flip it over, you can see that clear triangle right there. So we're going to do that on all 4 sides. Again, just to add some more structural stability. And as you're going through this, if you see some of the pieces don't look like they're taped down very well, you can go ahead and just tape them down a little bit more. You have as much tape as you want, so definitely use it. Also, I'm taping these kind of underneath the frame parts, just so that when we flip it over, it's going to be even. It's not going to be lopsided or anything like that. They can go on top, but that's just to make sure that it's going to be as flat as possible. And you can see these two didn't meet perfectly in the middle, but that's totally okay. You can just use another piece of tape. Again, it does not need to be perfect or symmetric. You really just want to get that basic shape in there somewhere. Okay, do this side now. To the corner. And down to the middle. Okay, and then the last side. And then tape these 2 pieces down. Okay, so we have our last pieces on, and now you can see when we flip it over, we have our frame with the triangles on the inside on every single side. So now that we're done building, we're going to test it. So I'm going to put it on our shake table, and I'm going to actually tape it down. This just helps it not slide off. It doesn't really help structurally, so if the structure is going to collapse, it's going to collapse anyway. So this just prevents it from moving around while we're using it. So I'm just going to tape the outsides down. If your structure doesn't have flat straws, you can still tape it down somehow. It might not stay in place as well, but it will still hold. All right. So now that we have it taped down, I'm first just going to test if it can withstand the lateral forces of the shake table or simulated earthquake. So You can see our structure stays pretty stable. It's barely moving, which is a good sign. So now I'm going to add some weight. The first weight I'm going to add is the smallest, 100 grams. We're going to add that to the top, and you can see it withstands. Also, we did add some Velcro just to keep the weight in place. It doesn't really matter if they have it on the wrong side or not. It still should be fine. The weight might just move around a little bit. So you can see it's fine with 100 grams. We'll try 150. You can see it still withstands that. We'll try our next weight at 200 grams. Still standing. And then our heaviest weight is 300 grams. And you can see it withstands that as well. So if it withstands all of those forces, then you can just add all of the weights, or you can add a small weight at a time. Mine is probably going to stand with all the weight, so you can see that even with all the weight, it's still standing. So thank you for watching. This has been a REACH presentation.